Hello everyone, welcome to course P27. This is resistance welding process metallurgical effects. Now, I'll confess that this particular slide you're about to go through is pretty much in every metallurgical program I've ever taught because it's absolutely the essentials. And if you want to understand metallurgy better, there's tool steel programs and everything contained within this website. There's one metallurgical for tool steels. I said it covers a lot of things that go far above what this program does, so feel free to check it out. So, metallurgical changes when it comes to heat. We have a material. If we have a metal in our hand, it has an existing structure. Now we know what this structure is. We can analyze this through metallurgical means. We can do macro analysis of the actual structure of the material. We can test it for hardness. We can test it for its mechanical capabilities. We can figure out things about this material, especially when it has a carbon steel as one of its carbon as one of its properties. There are other materials too that we can use that and I'm struggling not to go into the depth of that one. But if you wanted to go back to tool steel again, you could. But the existing structure is, what is it like in your hand right now? And is it ready for work or not? But the existing structure is usually in its toughest form, not its hardest or its most brittle, and not necessarily in its annealed or softest, but its existing structure. So when I have this in my hand, whether it's a tool steel or any steel, it can only get, and this is very important, it can only get as hard as the metallurgical composition of the material. We buy materials so they can be hardened. Sometimes we buy materials that are very hard, and then it makes it difficult for them to weld because they're so hard. But there's other things to consider. Okay, so the existing structure means it's in your hand, and now we're going to do the thing we always do. We're going to apply heat to this part. We're going to put it in an oven, or we're going to apply it. We're going to apply a torch to it. Maybe we're trying to do some heat treating on a punch or something. But somehow we're going to heat it. Now, there's something that I haven't put in this presentation called critical temperature. There's actually a certain temperature based on the carbon content in iron for steel, where you know, based on the carbon content, how hot you had to get it to wipe out all the existing properties of that material. So here's the important thing to know. I could have a piece of 1045, which is 0.45% carbon. And it's a little bit higher in carbon content. And I can do some incredible things with that 1045. I could make that as soft as possible. If I actually heat it very slow and allow it to cool very, very slow, I can put it in the softest situation. Or I can actually take that material, heat it up, and quench it. And when you quench, you harden. The carbon runs for the outside surface. It's looking for all this cool and running towards it, which means the outside surface is going to end up having a little bit more carbon content than the rest. So this is what we do, and this is how we make those changes. If we take a material, a steel, and we get it hot, there's a point at which it gets hot enough, and let's give it a temperature, 1333 degrees, which is if you have a carbon content of 0.83, and you're starting to have problems with it, you know that you can get it hot and then cool it off very slowly, and that'll take its properties away. Sometimes with our welding process, we come in and we hit it with a bunch of heat and then cool it very fast, and we can make things very brittle. And this is very common in HSLAs. That's why I'm always worried about it. So, based on the potential hardness for the piece of material, based on the potential, and that is its metallurgical composition, if we cool it quick, we'll get a harder structure. If we cool it slow, we get an annealed structure, or the slowest, we get the annealed, where it leaves it in its softest possible condition. There's all kinds of places to meet it in the middle of the road, but I don't want this to turn into a heat treating program. However, I do want you to know that if you start seeing cracks around your welds and you're welding something HSLA, or you're into dual phase materials, or you're doing something that's causing cracks, you have in your capability a way of adding a little bit of extra heat in a post heat while you've got a grip on this part. You could actually put extra pulses in it at the end to literally soften the structure and soften it enough that you've annealed it or normalized it or taken a bunch of the critical stresses out of this quench joint. And that's what it is. When you've actually taken this this cap and you've pressed it on it and you fired it for a certain amount of time and you leave it there, we already understand it's very important to keep the caps really nice and cool, but those caps can quench it as well. It can take it really, really quick. So I have lots, programmed many tail out, and I call them tail outs because my journeyman called them tail outs, is where in the final stages of its cooling, I actually gave it a little extra heat to slow the process down and leave the weld around the weld in a softer condition than you would normally get if you just left it alone. So that's all for hardness now. Thank you very much. Of course, as always, let me know if you have any other further questions. Thank you very much.